Good morning, everyone. My name is Sergei. I'm from Rescure in the Netherlands. I'm a security analyst. So I work in a security lab. We look at all kinds of devices. So I focus on smart cards, embedded devices, phones, tablets, all kinds of embedded systems. So that was the reason why I was interested in hardware wallets as well, because it's well, it's an interesting target. And today I will talk about two different research devices we took and the security we analyzed and the attacks we found to be possible on these devices. So before we go into security and attacks, just a few words about what is a hardware wallet if you've never used one. So it is a secure device. It stores your private keys on the device. The keys are normally to your cryptocurrency wallets. The hardware wallet connects to your PC or smartphone. It has trusted screen where it shows the transaction, what you're actually signing. You don't want to show it on your PC or smartphone because you don't really trust 100% your screen, what is shown on your PC because of all kind of software running there. It has trusted controls, so normally have a button, and this physical button is used to confirm a transaction. And it's on the device, so you can trust that when you press it, it's actually you confirming it physically. Normally, it has some kind of protected firmware. What that means is you cannot easily modify it, and there is normally some kind of signature checking happening on the device. And finally, the devices are tamper resistant. That means when you have physical access to the device, you cannot easily extract the secrets from the device. How does it look in real life? So there are a number of different devices. All kinds of manufacturers try to solve this problem of providing people with a hardware wallet. What you can see here, they look a bit different, but overall, they do have the features we mentioned before. What we're going to talk today the most about is two hardware wallets. They have quite different architecture, so that's Ledger Nano S. We're going to talk about software attacks on this wallet, and KeepKey, and we're going to talk about hardware attacks as we apply it to this device. So who is the attacker? Who would try to attack your hardware wallet? So it could be somebody who has access to your computer, somebody who can install malware on it, or another user of your PC. Why these people could be attackers? It is because they can send all kind of commands to your device when you plug it in, or because they can observe communication between your wallet and the PC. We're going to mostly focus on PCs today because both of the hardware wallets, Ledger and KeepKey, they connect via USB to your computer. Another possible attack vector is somebody who got physical access to your device. So for example, somebody who has access to a hotel room when you leave your hardware wallet there on the desk. Or somebody who steals the device and they have it in their possession, they can do whatever to it. And there's all kind of physical attacks possible. And finally, it could be somebody who has access before you got the device, before you initialized it and started to use it. So the supply chain attacks here. And it could be, well, it could be evil government who tries to control how citizens use cryptocurrencies. Or it could be previous owner if you bought second-hand device from somebody and they tampered with this and they changed firmware or they changed something on the device to later be able to access your private keys. And finally, before we go into attacks, what are the security features? How hardware wallets try to make sure that your assets stay secure? Well, first of all, the most important, your private keys always stay on the device. So normally, you generate the keys on the device. You store them securely there in memory. You use them in a secure way, so you sign transactions, but you never send the keys outside the device. And then when you're done with using your hardware wallet, you can wipe the keys, and then it should have no trace of the secrets you had. So that's the most important part. When you plug it in into a computer, it doesn't really copy your keys, so it always stays there. The second part is it has a very small API, and so there are only few commands you can actually send via the interfaces. And here, the simplicity is the key. You don't want to have a very complicated software running on the device, because then it's very difficult to make it secure. So I want to try to make it as usable for users and as secure to protect the assets. Then it has protected memory. So as mentioned before, it shouldn't be easy to extract the keys. It shouldn't be external memory when you can just connect to the wires and get the keys right away or something like that. And finally, the secure boot or some kind of protected bootloader is normally on the device. So you can verify, authenticate the firmware upon every boot and when you apply firmware updates. So that's are the features. And now we're going to go and see what are the software attacks possible. And we're going to take a look at a ledger for software attacks. So that's how the device looks like. You plug it in here to your USB port. On the left, you have the screenshot of the screen. It's just a Chrome extension. And you enter your PIN. You have 3 attempts to enter it correctly. And then you have multiple applications on the device. So what's important here is that this wallet supports multi-third-party applications, and they have their own store from which you can load a new application. And it supports like 5 or something, depends on the memory, how much they use. So how does it look inside? Inside of a hardware wallet of this one, they have 2 chips. So there is MCU, just a microcontroller, which mostly used as a proxy. So it handles the screen, it handles the button presses, it handles USB communication. And over serial here, it talks to the secure element. So MCU is not really a very secure chip, and it's used here. It doesn't store any secrets and used just to forward communication. You cannot directly connect to the secure element, the screen, because it only has serial interface. So it's a very simple chip, but it provides very high level of protection against physical attacks. On the secure element, you have Nano S, a very, very simple operating system. It is a trusted execution environment. And you have a number of applications, which we've seen before in the previous slide. You have a number of different applications installed. And this dotted line here, it means that your operating system of the hardware wallet on the secure element, it is meant to provide isolation. So the idea is you do not really 100% trust every wallet on the device. And if one of them is compromised or is malicious, you don't want them to cause security issues to other applications or to the operating system itself. So it's similar to the approach of all the operating systems, your smartphone, when you install apps from App Store and so on. But so are they really trusted? What can we do as an attacker when we have our application installed? So the nice thing here is that manufacturer provides an SDK, so you can make your own applications. You can install them on your device. You can see what they can do. The way it looks like when you install it on the device, so you have operating system, and your app is in memory. So you get some memory, you get flash when you install the application, and you get some RAM memory. Normally, by default, you get like 16 kilobyte of flash and 1 kilobyte of RAM. And there's memory protection unit, and it is meant to make sure that your application can never access memory which is not meant to access. So for example, you cannot access operating system memory. You cannot access memory of other applications. And of course, you have to have syscalls, because if you want to do some more advanced operations than just simple commands in your code, for example, when you want to compute hash of some buffer, or when you want to use crypto engine, hardware crypto engine, you will send the syscall to the OS to do that. And then OS verifies if you have rights to do this on this memory. Which is also very nice attack surface. You have more than 100 system calls. A lot of them take multiple parameters, so there's a lot to explore there. So that's, we found a number of vulnerabilities on the device, 7 in total. Some of them, like the system call related ones, they resulted in some memory disclosure of operating system and other applications. But we're not going to really focus today on that. We're also not going to talk about supply chain attack, which was possible in the device. We'll just talk about 2 as an example, what you can do, and why it often happens that your small security issues on the device can result in a bigger attack. So we're going to talk about debug applications and the wipe process. So what is the debug app? So we've done this research black box without knowing how the OS works. OS is a closed source. Manufacturer does not release the source code, so you don't really know what it does exactly. The applications, though, they are open source, so you can see their code, but not the operating system. And that's something you can see in SDK. That's what it says. So you can install debug app, providing this flag when you install it, when you install your application, and then you can dump some core ARM register. It's not very detailed description. You don't really know what it does, but you can try that, install, and see if you can access some extra memory or some registers and so on. So that's what we tried. And so what we found out is that your debug application, due to misconfiguration of memory protection unit, could actually read more memory than it's supposed to. So normally when you have your application here, you have boundaries of this 16 kilobyte, this is flash memory, and that's what you can read. If you try to read something outside, you get an exception. What happens to debug app? It can actually read a bit more before the application. The application is also installed sequentially on the device in flash. They just follow each other. So if you install a debug app, you can read memory of another application, which is well, very convenient. So you can dump a bit of flash. The nice part, you can also repeat this process. You can do it. You can delete the previous application, install a debug application again, dump a bit more of the memory, and continue it again, and even dump system flash. So that's a nice thing that we can do that. That's clearly a security issue because application not supposed to access memory of other applications or the system. But all you can do is read a bit more of other apps. And the problem here is to install application, to install your debug application, you need to know the pin code. But if you know pin code, what's the point? Like you already have pin code, you can do whatever on the device. So that issue is not that big on its own. You cannot really exploit it in any real-life scenario. But the next issue we found is the wipe process. So that's something I would like to show a small demo on the video, if it works. Yes. So what you see here, that's the device. So first, we're just going to unlock it with the correct pin. And you can see that there's a number of applications already installed. This is our own application. We just call it EvilCoin. That's our what we installed there. So that's what you had on your device before. Then if you enter your pin 3 times incorrectly, you can think of an attacker who stole your device. They try to unlock it. They try to guess the pin. And they fail 3 times. What is going to happen then, it is going to show that you reach the attempt counter, and the device is going to be wiped. So that's what can happen to anybody. Once you install the device, you don't need to know the pin. You try to guess, you fail, you reset the device. What happens then? Once you fail to enter the pin, it resets the settings. You see it's flipped now because it resets the setting of the screen orientation. And then it tells you to configure if you would like to configure the device as a new one. So you can set a new pin which you want to use. It said it already wiped itself. And then it just shows you the generated set of words. This is your sentence, which corresponds to the master seed. So that's your main secret. But what you can see after reset, you can see that the flash is still there. So although they wipe the device, so they wipe the master seed, which is used to derive the keys. For example, your Bitcoin or Ethereum application is going to derive the keys at runtime using the master seed, which is wiped, so that you cannot really attack. But you can see that at least flash is still there. So what can we find in flash? Is there something interesting, or everybody derives their keys at runtime? If they would, then, well, that's also not much we can get. But what I mentioned before, we have open source application. So for example, this is a second factor authentication app, which manufacturers also provided. And you can see this application uses non-volatile memory write system call to write HMAC key in Flash. So what it means, if you have this application and you used it, what is going to keep in Flash is the HMAC key of your second factor authentication. So an attacker who can do what we just showed before, who can steal the device from you, who can try to guess the PIN, if he succeeds, unlikely, but well, possible, then he has full access to the device. If he fails, he can try to initialize devices new, install debug application, and actually read the memory, including some of the secret keys on the device. So that's one of the examples. We also found that some other applications use this method of storing the private keys or secret keys. For example, Monero application, which was beta at that moment, they also stored the key in Flash. They couldn't derive it at runtime. Or PGP application also stored the key in Flash. So you can see here that two simple bugs, which are not big deal on its own, well, they're bad, but they cannot be exploited right away, combined together could lead to a real-life scenario attack. So that's something we'd like to show today on hardware wallet software attacks. What would be the conclusion of this talk? Well, software cannot be trusted. No matter how hard you try, you always have bugs. You just need to try to manage it in the best way you can and try to limit the attack surface of an attacker and well, handle the bugs as they come. Well, is it the end for hardware wallets? That's not yet the end. So that's another case I would like to show what you're going to do if you cannot find a software bug. So if there is an exploitable bug, that's easy. You can just exploit it, and you're done. But what if there is nothing you can find? Does it mean that the hardware wallet is secure against any attacker? So that's another hardware wallet. That's KeepKey. It has a bit of different architecture. So it has only one chip, unlike previous one, Ledger. It only has STM32. And this is just a microcontroller, which is quite common to all kind of IoT devices. It's not meant as a very secure device. It just, well, it's good enough for some purposes. So there are a number of commands available for you to send from your PC via USB to the device. And it is fully open source. You can see firmware and bootloader on GitHub. You can have all the code you want. And it has protected boot the same way as we mentioned before. So upon boot, they verify signature that you execute exactly the code which you meant to execute. So you cannot just easily change it to something else. How does it look? You can see here you have similar picture. This is the sentence for your backup, which corresponds to the master seed. And that's your PIN. So you actually type your PIN from your computer. It only has one button here to confirm transactions. But it is scrambled, so your malware cannot easily figure out what's your PIN because you just have to see the randomly scrambled PIN, and then you enter from your PC from the numpad, and then you're unlocking your device. That's for the way it's used. It's not very big difference here. So that's the chip. You have single chip, as we mentioned, STM32. It has internal flash, so you cannot easily read the memory. The flash is protected so you cannot connect with a JTAG or something. Here's the layout of your flash. So it has some secure storage, it has bootloaders, it has firmware, all within this 1 megabyte of flash internally on the SOC. So why would we try to use a hardware attack on this device? Well, it is a popular open source project. So a lot of people look at the firmware. They have a bug bounty, so a lot of people reported bugs in the software. It was patched over time. All the easy issues are solved. And it has a microcontroller, general purpose MCU. So it's not really very secure against hardware attacks. It was not developed this way. So that's exactly the place when an attacker can try and use some of the hardware attacks. What can you do with hardware? So what we're going to talk about today briefly is what is fault injection or glitching. So normally your hardware expects to some conditions to execute properly. For example, it expects a stable clock. It expects normal voltage. It expects that there is no EM pulses happening around. Nobody shoots laser at it, or nobody sets it on fire or puts it in a freezer. So that's a normal condition of your device. That's how you want to use it if you're a user. But for an attacker, you don't really have to do that. You can do anything to the chip and hope you can get some secrets out of it. So what normally happens, for example, you can provide very unstable clock on some devices. And that would mean that sometimes there are corruptions happening. If you can control your glitch precisely, so doing it for a very short time for this exact instruction which is executed, then you can just try to affect this specific instruction you want to bypass. And normally what happens is you can corrupt data on the line. If you do it in a specific moment for very short pulse, you can just corrupt 1 or few bytes of data when it's read from memory or written to memory. You can try to similar way corrupt instructions. So instead of executing one assembly instruction, it's going to execute another one. Or you can try to skip instruction, which is just one of the cases of corrupt instructions. Because, for example, if you corrupt move instruction R0 to R1 to move R0, R0, you're just skipping this instruction. So doing nothing for this clock. That's most common corruptions which you can expect. And you can normally expect it with all kind of fault injection methods. So for example, if you use clock, if you use voltage, if you use AM or laser, normally you can see more or less similar picture. It's not as precise, all of them to the same level. So what we're going to talk today is electromagnetic fault injection. So first thing you do if you want to try to use a hardware attack, well, you need to open the device. You can see the awful job I did here, almost broke the PCB. I want to try to open it. But well, when it's out, job is done. The most difficult part is over. You just build the setup like that. That's a horrible mess I had on my desk for like half a year while playing with this. What you see here, you have your glitcher. That's the device which actually creates EM pulse. There is a coil on top here and just a bunch of capacitors. There's another device which provides signals. So it's pretty much a fancy FPGA. It provides a very precise low jitter signals. So you can specify exactly when you want to send the signal. And there's XYZ stable, so later on this glitcher goes on top of XYZ, so you can move precisely on top of the chip to try to glitch it. And the device there itself in the middle locked in XYZ stable station. And there's a scope if you want to measure the signal and see what exactly happens on the device. So we have the device, we have the equipment to glitch. Where do we glitch? So we need to decide when exactly do we need to send this pulse. And of course, as an attacker, you know only so much about what actually happens on a very low level of your hardware. So you see that this is D+ line of your USB. When you send commands from your PC, you can see here the command, and here the response you get back. And there is 1 millisecond in between. And somewhere here is happening the operation which you want to try to glitch. We're going to talk later what exactly we try to affect here. But for now, so you don't know when exactly. You cannot find it better. So what you can do is try to brute force these parameters. So you just try to glitch with different offsets. You start here somewhere from the command. You wait for some clocks. And then you try to glitch there and see what the results are. And then you try to optimize the parameters to get the best out of it. So what do we see? So that's a picture of full scan of the chip with some simple commands. So that's characterization. That's what you often do when you try to use fault injection. So what's used here is a simple command. So hardware wallet provides you with a command ping, which is just you send the string and you get the string back. So I just send a hello world and I get it back, and that just means it works as expected. And that's the green dots here. The yellow dots on this picture are the ones when you send the command, you attempt to glitch with the specific parameters in this location with a specific power and specific delay from the command you've sent. And what happens, there is no response. So the yellow dot means you just muted the device, maybe corrupted too much, or the corruption is not really a good one. So the way you affected it actually result in a reset of the device. And the most interesting ones are the red dots here. You can see a few on the left side and on the right side. And what they correspond to is the actual corruptions. So you send this string, a specific command for this case, and you get something back, but it's not what you expected. That's not the string you've sent for the ping command. It's just something different. And that's what we want to do. That's the kind of effects we want to have on the device to try to change its normal execution to what we try to affect. So I'll just show a small video here of the process just to give some feeling of how it works. This is not in the XYZ table anymore. Just took it out to see if I can be as effective just moving it by hand. I wasn't. But you can see here the glitcher here on the horizontally. This is the FPGA. And you can see here the commands we send. So the green light, it's barely visible, but the green means that it just the string we get back is what expected. And yellow is that there is reset. And that's the USB communication, I believe. And that's the command we send. That's where we glitch. You can see the spike here on the line as well, because we just provide more voltage or less voltage there. And you can see when we glitch it too hard, there's no response. But when we glitch it just enough, there's still response back. But we try to affect it in a specific way. So that's the process, more or less. And then all you need to do is to try to find where you want to glitch and what are the parameters of your glitch. What are the parameters of your EM fault injection to change the specific command. So there are a number of outputs on the screen as well. So that's not the glitch we want, but that's something we get. So the one on top, it says error detected, reboot device. That's something manufacturers implemented. So they read something from flash, and then they do CRC on it just to check that the data read correctly. And that's what we affect here. So we pretty much corrupt the data read, which results in an incorrect CRC check. So that's not a good glitch, but that just shows that it have some effects on the read from flash. Another one says clock instability detected, reboot device. What happens here is that hardware wallet manufacturers, they implemented some simple check on the clock register. So they actually verify that your clock is working as expected. So if you try to do a clock fault injection, that might not be working because of this check. But as we're trying to do EM, that's not something we want to do. Sometimes we affect the clock register, but we try to see other glitches. A few more examples of what can happen. Here you can see that we probably corrupted the XY of the output screen, so where the screen starts. And you can see that it actually wraps around and prints the message in a glitched way. So it can happen on all kinds of screens. It's quite a common corruption. Also not very useful for an attacker. You can affect the screen, but it's not something you want to do. So what do we want to do then? What is the exploitable glitch we would like to execute on the device? So that's, as I mentioned before, it is fully open source, which is very nice for an attacker. You can just see the code, see exactly what you want to avoid, and do that. So you can here see one of the commands. It, 1 second. So that's command reset device. You can send it from your PC. It takes a message which you provide in the buffer. And first thing it does, it checks if your device is already initialized, which makes sense. If you already initialized your device, you shouldn't initialize it again. So it says if you want to initialize it again, you need to wipe it first. If you wipe, you lose all your keys and PIN code and the rest. So that's not something we want to do. We don't want to really wipe the device. We want to skip this check. And what happens if we skip this check, this if statement? Then this is not going to be executed, and the following code is going to be executed. So what is going to happen is that it will do init of the device with the PIN you provide in the message. So you can set a new PIN, or you can set if you want to have PIN at all or not. And then you can put it in the message and try to glitch this if check to skip it altogether and change the PIN on the device. So that sounds easy. And once you have the setup, which is ready to do the glitching as we've seen before, all you need to do is you send this command again and again, and you provide set the PIN to a specific value which you want to have it after, and you try to skip that. If you see that this message is printed, it means that you would like to try again. If you see that it applies these changes, then, well, you're done. And that was one thing. So first, you can send reset device, but then it's only going to change your PIN in RAM. It's not going to change PIN in flash. So that's could be enough for us, but it's not persistent. So if you just reboot the device, then you don't really know what's the PIN there, and it's going to be loaded into RAM again. So you can only use it for one boot. What we would like to have is the persistent change of the PIN. So what we do here, we send the reset device command, and we try to glitch here many times. And we need only one successful glitch. One glitch would actually change the PIN in RAM. And the second, we can send change PIN command. And it expects you to know the PIN, and it checks it again, PIN in RAM. So all we need to do is to reset the device, set PIN in RAM to the value we know, then send change PIN command. We don't need to glitch anymore because we know the PIN in RAM. We authenticate using this PIN, and we provide new PIN, which is written to flash. So then, in this, with a single glitch on the device, we are able to change, and two commands we send, we're able to change the PIN in flash. How does it work? Well, a bunch of words here. We can just see it on the picture, the same scenario. So your attacker, again, gets physical access. So they found the device, or they stole it from you, or anything they could do. Then they put it in the setup. They send reset device command, and they try to glitch again and again until it's successful. Once it's successful, they change the PIN in RAM. Then they send this command, no glitching is needed anymore. They change PIN in flash, and, well, that's the end of story. So you still have your private keys on the device. It wasn't wiped because we skipped this check. We didn't send the wipe command. But it has a new PIN now. So you have full access to the device after the successful glitch. What were the results? Once you find the good parameters, a good spot where you want to glitch, more or less good timing when it happens, and you try to repeat it, the success rate is 1.2%, which doesn't sound like much, but it's not like success rate that out of 100 wallets you can glitch one. It's a success rate out of 100 commands you send to this wallet. One of them, on average, will be successful, so it will change the PIN. And you can repeat this many times. So on a single hardware wallet I had, I've done more than a few million glitches. It didn't ruin the device, so it's still working. So temp rate is not very high because it boots every time. It verifies all the signatures, so it's quite slow, but still fine. Overall, in 5 minutes, with this success rate, you can change the pin once you have good enough parameters. So that's the result of the second study. So we've seen today the software attacks. Software cannot be really trusted. That's what we've seen with the logical attacks. And you have to try, if you make your embedded devices, try to make it as secure as possible, to have some firmware update mechanism so you can change and fix the issues which are found, and use somebody's help. So maybe you can ask third parties, you can ask, have a bug bounty, and have people who actually try to help you with this issues. So also maybe good to mention that these issues we found, we reported it to manufacturers. They also have bug bounties, and they try to fix it. So these issues should be solved on the latest updates of the devices. And finally, hardware. If you have your secure hardware, you cannot really trust it 100% of the time. If your attacker is able to spend enough money, they always have more advantage than you. But there are still some things you can do. So you can implement some countermeasure. You can use more secure hardware. There is specific hardware which is meant to be used for these cases. And you can implement more advanced checks in your software as well. So that is it for my talk. Just an interesting picture. One of the glitches I had on the device is what happens here. It probably corrupted the pointer to the string it wants to print. So it wants to print here something like, maybe there is a ping command and says the message is this and that. But instead, it corrupts the pointer to the string, and it just prints a random place in memory, which doesn't have really ASCII printable characters. So you can see these sad faces. That is it. Thank you for your attention. And if there are any questions, I will be happy to answer now or after the talk somewhere.
ありがとうございました。